2. What did I say that? What did I say the two purposes of resistors were used for? Yeah, one to limit our current and then to divide our voltage. So then Mike, I don't know if I can remember how he worded it. Were you talking about what would happen to if I keep on adding
resistor after you
Yeah. So here's our here's another little troubleshooting thing then. So what happens to my voltage across R1 as I keep on adding another load to my voltage divider? What happens to my voltage across R1 as I keep on increasing another load? It's going to get higher, right? Because this here total resistance is going to start to go down, right? A parallel circuit, as I add resistance to a parallel circuit, the total resistance of that parallel circuit is going to start to go down. So that means that R1, the voltage is going to start to go up. So if I keep on adding a load to my circuit, and my voltage is going to go up, what also happens to my power? What's that going to do? Increase, decrease, or stay the same?
Increase.
That's going to increase. Okay? So on this one here, we are at 139.5 watts. So, let's say that this resistor here was only rated at 150 watts. Okay, a big watt, that'd be, about 150 watts is about this size resistor right here. That's about a 150 watt resistor. Okay? Well, if I keep on adding too much loads onto my circuit, what's eventually going to happen to my resistor here?
It's going to open up.
It's going to what?
It's going to burn out.
It's going to burn out. It's going to open up. Okay? So yeah, I didn't load down the circuit too much. Now, if we properly design this circuit, what we do is that if I keep on adding the most amount of load that I could ever put on this circuit would be to put a direct short on it, right? That would give me a direct short, right? I'm just taking this test point and I brought it right to ground. I just shorted it out. Because what do I measure across the short? How many volts?
0.
0 volts. So that means I just brought 0 volts to this test point. That's the same as, because what's the definition for my reference point? Yeah, plus or minus 0 volts, right? So I basically, literally, my output now is that plus or minus 0 volts. I essentially just tied my test point to ground. They're both at ground. So what we do then is when we're designing these circuits, is that since R1 is going to do two things. It's going to limit our current, and it's also going to divide our voltage. So if we have a 10 volt power supply, let's say, if I didn't have this resistor in there, there's a good possibility that I could damage my circuit if I put a short across my power supply. So to protect our $500 pieces of equipment, we put in a current limiter resistor in there. And so what we do is that we treat it as what would happen if I ended up shorting that output directly to ground. And then what I want to do is calculate out what my voltage would be. So I know that with this being shorted out, with this test point being shorted out to ground, I got a 10 volt source. What would be my voltage across R1 now?
10 volts.
10 volts. Okay? So that's going to be the worst case that this resistor is ever going to see, is that it's going to get the maximum amount of voltage. It's going to be 10 volts. Now we know two things, right? We know that this resistor is rated at 150 watts. It's rated at 10 volts. What's my current going through it? How much current do I have going through my resistor?
Well, it's dependent on what the resistor's rating is.
15. What's its value?
Well, we know that, well, let's take a look. Do we have enough information to find it? So we know that P is equal to what? IE, right? So we want to try and figure out I, right? So what would I have to do? If I know my voltage and I know my power, right?
Short of that.
So what could I do then to come up with my current? How would I manipulate that formula? Yeah, divide each side by E. So P divided by E is going to equal what? I. So what's P divided by my E, or my 10 volts?
15 amps.
What is it?
15 amps.
15 amps. So now I know my 15 amps. Now do I know enough information to calculate out what resistor I would need? So what size resistor would I need? What is it? So what's 10 divided by 15? 2/3. Okay, what's that in the proper measure prefix? 2/3 milli.
666.7 milliamps.
Yeah, 666.7 milliohms. Okay, that's the size resistor you would need for that circuit to treat it as a dead short. Okay. So pretty small. So typically, we don't want to, all we're using it is just to limit the current. Typically, you wouldn't have such a high resistance on that. That's pretty small, but I was just using it since it was up there. But typically, R1 is typically a smaller resistor than what our voltage divider is. It's just enough to limit our current, just to protect us from a dead short. So then,
We use 15 amps.
so now, let's continue on. So now we treated it as what a dead short was. Now we know that we want a 667 milliohm resistor. So let's figure out what we want R2 for. We know that we want a voltage drop. So let's say we want to drop, let's see here, what would be a good number. It's going to drop. Let's say we want a output voltage of, let's just go with 8.5. I don't think that should be too bad. Let's say we want a positive voltage of 8.5 volts unloaded. So now what would have to be the value of R2? So we know that 8.5 volts is going to drop across R2, right? Now, how much voltage, now I'm going to take care of this because that was under our shorted. How much voltage is going to be dropped across R1 now?
1.5.
1.5 volts. Okay? We're going to keep this. We want to keep our 600 because we know that we calculated out our 677 milliohms. Okay? So we know that, now we know our two things, right? So we know that R2 is going to drop 8.5 volts. We know that we already calculated out our worst case scenario for R1, so we already have our resistance and we know what the new voltage drop is going to be. Now what's my new current going through there with that voltage divider not being loaded down? So what would be my current now?
No, 2.250.
2 point what?
250.
2.250.
Yeah.
2.2
Amps.
Yeah.
Not amps, so it's not going to be amps.
Oh, because it's milliamps.
Yep, it's milliohms. So what's that current going to be?
We reduced that.
Yeah, so it's 1.5 volts divided by 666.7 million. Does it equal to be?
It is.
Okay, I just didn't, a little bit too large, but okay, it probably is because it
Because of
isn't.
the decimal point where that is.
Yep, okay, so 2.5, so now we have 2.25 amps now. So now, what remains constant in a series circuit? Current. So how much current do I have going through R2 now? 2.250 amps. So now what's the value of R2 now? What is it?
3.778.
3.778 ohms?
Yep.
So 3.778 ohms. Okay, so now that I hook that up, now that would be what I would get for, so to get an 8.5 volts out of my output, these would be what I would make my two resistors. I'd make them as 667.7 milliohms, and 3.778 ohm resistor. And that would give me an output of 8.5 volts. But at the same time then, is if all of a sudden I took this output and I ended up shorting it out, this is going to drop down to 0, this is going to go up to 10 volts, my resistance stays the same, it's going to go up to 10 volts, my current's going to go up, and I'm going to still be within my 150 watts, and I'm going to still protect my power supply. I go ahead and I remove my short, and my voltage goes up to positive 8.5 volts again, and my voltage divider works just as normal. And then since we're talking about that, and then so if I have, since this is a pretty small resistor, we really actually, this is a pretty strong voltage divider. This is what we call a stiff voltage divider, meaning that it really would take a lot for me to change it. If I put in something 10 times larger than that, I can almost put down I can almost put in a 37 ohm resistor in here, and that voltage would hardly affect it because this one's so small compared to this one. This one's 10 times smaller than this one, that my voltage would hardly see a change. If I were to put something that was closer to this value here, a 3.778 ohm resistor, now my voltage is going to really drop because my current's going to divide up, my resistance is really going to drop on this parallel circuit, and my voltage would really drop on my output. But if I have something that's 10 times larger than that one, it's not going to affect my voltage very much. It will drop it a little bit, but since this resistor is so much larger, I wouldn't have any effect on it. It would be like if I had, if I have a positive 8.5 volts here, and if I put my voltmeter in there, this is all part of chapter 6 here. They talk about this. If you did your reading, you'll know what I'm talking about. But if I put my voltmeter in there, I'm going to measure 8.5 volts. Even though I'm putting my voltmeter is basically the same as a resistor. Okay? But the difference is that this resistance of this voltmeter is 10 megohms. Very large compared to this one here. So when I put my voltmeter on there, it doesn't change my voltage. But if I did end up putting if all of a sudden I put in a very small resistor, now remember our total parallel resistance is always going to be smaller than our smallest resistor. So if I put something in there very close, so to 3.778 ohms, this parallel resistance now is going to cut down by half. If that resistance cuts down by half, my voltage is going to go down, then meaning that my output is going to go down. How many people follow that? See, be careful of the questions you ask, Mike. Yeah, those are good questions, though. These are the things that we deal with all the time, though.
Would it be more of a semiconductor than a resistor?
No, that's not a semiconductor. No, don't go there.
Very low resistance.
No, it can be any type of resistors. But yeah, we do have what we call the loading effects of our voltmeter. But when we do work with semiconductors, because we're going to be working with microamps and nanoamps and stuff like that, what actually can happen is if all of a sudden my since Mike took us over to the solid state.
Way to go.
So what happens is that because if I have 10 megohms of resistance going across my ohm meter, I'm going to have a very small amount of current going through there. It's going to be 8.5 volts divided by 10 megohms, but I'm going to get a certain amount of current going through there. So it's kind of funny if all of a sudden, let's say for some reason, if all of a sudden R2 opened up, and we'll just put something simple as an LED. Light emitting diode. Okay, that's a solid state device. Okay, it emits light as we. Okay, so it's kind of funny though. This is what really, if we were all in digital, I would try to talk more about it as being a digital circuit. So I'm going to just use an LED so we can see what would happen. So we'll just say that R1 opened up, or R2 opened up, and my light isn't lighting up. So then I go ahead and I put my voltmeter in there, and I'm going to check for voltage across my output to see if I got any voltage. So all of a sudden I put my voltmeter in there, tied to ground, that's the same as me doing this. Here's my voltmeter. Now what happens is that I'm measuring across an open, I'm going to measure my source voltage of 10 volts, but what also happens is that all my current is going to come down, it's going to go through my meter, back up into my circuit, through my resistor, into my diode, it's going to bias my diode, and all of a sudden my light lights up. So all of a sudden I'm trying to figure out why every time I hook up my voltmeter up to my circuit, and all of a sudden my circuit turns on. I remove my voltmeter, and it shuts off. That's because I actually start drawing current through my circuit just by putting in a voltmeter. And it really can affect it if we're doing digital circuits because it doesn't take much current to turn on a digital circuit. So all of a sudden you'll be working, nothing's working, and all of a sudden you go to check something, you put a voltmeter in there, and all of a sudden everything starts working. You remove your voltmeter, it stops working. It's because you just made your path with that voltmeter in there. And it's caused by solid-state devices, and especially nowadays it's even more critical because everything is such small amounts of current that we use for driving that circuit.
Sounds easy to
Well, then
find.
you can depend on that for troubleshooting.
Yep, you can, because then you know that you're probably put your voltmeter across an open.
Yeah.
And now you know what the problem is, that one resistor probably burnt out.
Creating a short and bypassing the
Yeah,
problem.
not creating a short, creating an open.
But he's talking about creating a short through.
With the voltmeter, yeah. You didn't really create a short because this is 10 ohms of resistance, but you created the path.
Yeah.
Yep, you created the path.
But you isolate the problem.
Yep.
You close the circuit.
All right, good questions. I like those kind of questions. You ask them and I'll tell you. Yep. So if you want to get out of here on time, then keep your mouth shut. All
We want
right.
our money's worth.
Yeah, that's right. I want to make sure you get everything that you got coming to you.
And then some.
And then some. And then I'll even give you some that you didn't even ask for. All right. What was that?
Oh, he told me to hush up.
Oh. Yeah, good questions though. I like those questions. So that explains a lot about chapter 6. So if you did end up reading chapter 6, then that all makes sense. If you didn't read about it, I'd recommend you read chapter 6.
No.
Then you understand what I was just talking about.
Oh.
Yeah. All right, so let's, we got 10 minutes here. So what I want you to do is go to worksheet number 1. Sometimes the hardest part is just trying to straight line these. So work with the guy next to you, work with the other side of the room. But the first thing you want to do is you want to make sure that you straight line. Again, if you read all, make sure you read all my notes. Straight line all components, test points if possible, sketch an electron current path, indicate polarities and components. Make sure you do all those.
Which number one?
So just go ahead and, to begin with, just go ahead and start straight lining that. And then once you get it straight line, start trying to do your equivalent circuit.
Is that the series parallel circuits?
Yep, that's